Good news, there's a shortcut to all of the chi-dist stuff with degrees of freedom. Excel has a function called chi-test where you give it the block of your observed values and the block of your expected values. That's chi-test rather than chi-dist. It then computes all the individual components of the chi-squared value, adds them up, computes the degrees of freedom, and then uses chi-dist for you. It gives you whatever chi-dist gives back, so the p-value. You still have to make that table of expected values though. So here we've got our original observations, we've got our expected values computed the same way as before, and then chi-test, you tell it here's my observed values, here's my expected values, and it does all that and gives you the same p-value we got before. You might be wondering, do I have to give observed and expected in the same order, or can I just switch the order? It does make a difference because you're dividing by expected rather than observed. So that's a quick way to do a chi-squared test, and it computes the degrees of freedom based on the size of the table, 2 by 3 or 5 by 9 or whatever. Another nice shortcut is lock5 stat, and that computes the expected values for you and the chi-squared value, but then it doesn't do the chi-dist, it does it based on randomization. So here we are at stat key. We're going to use the chi-squared test for association. And this is just some built-in data. We're going to say edit data and hit, click there, hit Control A or Command A to highlight everything, and then the backspace to delete it all. Over here in Excel, I pre-formatted the table. It wants no spaces in the names of the columns and rows. So I did that and paste that there, and this is not raw data. You can actually have it kind of do the pivot table for you if you have the raw data, and we do have a header row there, so I say okay. So that's the table. It computes the chi-squared value. That's the same one we got. If you say show details, it gives you the contribution to chi-squared. Those are the squared values already in blue, and it shows you the expected values in the middle in green. And then to figure out what your p-value is, you'd say generate one sample, and it will randomly resample from this table, but in a way that will make the two variables independent, but still keep the same marginal totals. And then compute the chi-squared value for that, and then record that new chi-squared value. And then if you do that 1,000 times, you get something like the chi-squared distribution that we had seen before that was very right skewed because our degrees of freedom is very small, although this doesn't really need to compute degrees of freedom. So do that a few times. I'd say 10,000 is the usual standard. And then say show me the right tail and put in the original chi-squared value, and that was 1.386. And it shows you the number of those 10,000 re-randomizations that gave a chi-squared value equal to or greater than that, which is 0.59, which is kind of the same as this, but you can see that we didn't really have a nice smooth distribution here. In the table of expected values, and we saw this in the other table too, some of these expected values weren't above 5, so we're not getting a nice smoothish curve here. So in fact, if your expected values aren't above 5, one thing you can do is do a randomization-based test like this, which isn't assuming that the chi-squared distribution is all nice and smooth. So that's another way you can do a chi-squared test. Hypothesis tests are okay, but the field is trying to move more toward confidence intervals, so is there a confidence interval version of all this? Well, for a 2 by 2 table, you can say, let's do a confidence interval on the difference of proportions, just like you could do a confidence interval on the difference of means, like we did in chapter 11. But for a 2 by 3 table, or 3 by 3, or 4 by 3, or whatever, you can't do just a single confidence interval, because you can't take a meaningful three-way difference to get just one number into a confidence interval on it. So that's kind of sad. So another weird thing is that the chi-squared test can say, yes, there is association in this table, but it can't pin it down to which column or which pair of columns or trio of columns is actually causing it. That's because it's trying to do it all at once. So you have to ask yourself, is the chi-square test actually answering a question that I think is important of, is there association in this table without telling me where? For a 2x2 table, it's pretty obvious, but for anything bigger, it's time to think, do I really need to be asking this question?